Greetings to all of you. It's a privilege to be here today. My name is Aleksei Babenkov, and I bring over 8 years of experience in data science and machine learning. I work as a senior data scientist at Avito, which is not just a large classified website. It's the largest in the world, serving about 60 million users every month. At Avito, I contribute to maintaining our search engine and occasionally recommend a system. Our search engine processes thousands of queries per second and generates about 1 terabyte of raw data daily. We store this vast amount of data in systems like Apache Hadoop, and we analyze it to find useful patterns for building and refining models that improve user experiences on the platform. My expertise lies in natural language processing, search algorithms, and recommender systems. I predominantly use Python for research and development, while Golang and a bit of C++ are my go-to tools for deploying these models into production, ensuring efficient performance and scale. Today I'm excited to share with you how we can use Numba to accelerate Python in scientific computing, which is vital in managing large scales of data we work with. Python's flexibility is fantastic, but its performance can be a bottleneck, and Numba offers powerful solutions to these challenges. Python has quickly become the main language for scientific computing because of its easy-to-understand syntax and strong set of libraries. Whether it's predicting when your pizza will be delivered or exploring the secrets of the universe, Python can do it all. It includes tools like NumPy for maths, SciPy for scientific tasks, and Pandas for analyzing data, making it easy for scientists to handle complex problems. Its importance is also seen in the trend of using Python notebooks in academic papers for reproducible research. Driven by a community-led development model, Python continuously adapts and grows, staying vital for scientific inquiry. This dynamic community helps push scientific discovery forward and make sophisticated computing tools available for everyone. To better understand Python's performance, it's important to know the basic differences between compiled and interpreted languages. Compiled languages such as C or C++ convert all their source code into machine code before the program runs. This conversion, called compilation, is done only once, which allows the computer's processor to run the code directly. This is why programs written in compiled languages generally run faster. In contrast, Python is an interpreted language. This means that Python code is processed step by step by an interpreter at the moment it needs to run. The interpreter reads each line, converts it into machine code, and then executes it. This step-by-step process provides great flexibility and makes it easier to write and test code, but it also adds extra steps that slow down the program. This key difference explains why Python, despite being powerful and versatile, may run slower than compiled languages. However, tools like Numba are designed to help overcome these speed challenges, and they optimize Python's performance. To understand how Python operates, let's take a closer look at the Python interpreter, which is essential for running Python code. Python uniquely blends features of both interpreted and compiled languages. Initially, Python code is converted into abstract syntax trees or ASTs. These ASTs are then turned into bytecode, a simpler platform-independent format somewhat akin to what compiled languages produce. However, this bytecode isn't the final machine code that computers execute directly. It is processed by the Python virtual machine, which interprets the bytecode at runtime. This additional step means that despite an initial compilation phase, Python depends on a PVM for execution, which can introduce some delays. The process involves several steps: passing the code into ASTs, compiling this into bytecode, and interpreting the bytecode. Each step adds a bit of delay, unlike languages that compile directly to machine code. This is why Python can appear slower for tasks requiring high computational speed, prompting the use of tools like Numba. Numba helps by compiling Python functions directly to machine code that your computer's hardware can execute more quickly, thus minimizing delays caused by the PVM and enhancing performance for demanding tasks. As we explore how Numba accelerates Python, let's first look at LLVM, the system it's built on. LLVM stands for Low-Level Virtual Machine, a key tool in modern programming that transforms high-level language code into optimized machine code. The main strength of LLVM is its ability to make detailed improvements across the entire program. This is done through somewhat called LLVM intermediate representation, or LLVM-IR, which helps LLVM analyze and fine-tune code, regardless of the language it's written in. LLVM is flexible, supporting many programming languages thanks to its extensive range of components. LLVM is essential not only for languages like Rust and Swift, but also for making Python faster with tools like Numba. It's especially known for working with CLang, a compiler famous for its speed and how well it works with C and C++. With LLVM's help, Numba turns Python code into quick, runnable machine code. Let's look closer at how LLVM enhances performance. LLVM does more than just translate code. It completely changes it to run better and faster. It goes through several steps where it optimizes the code, making it more efficient across different programming languages. This is done using something called LLVM intermediate representation, which acts like a common language inside LLVM, helping truly optimize the code before it becomes final machine code. This optimization greatly improves how fast programs run, making them work well no matter the language or computer architecture. For Python, using Numba with LLVM's capabilities significantly speeds up Python code, often matching or even surpassing the speeds of languages that compile directly into machine code. Integrating the power of Numba into Python is surprisingly straightforward. By simply installing Numba with a pip command, you also automatically download LLVM, which is a core component that Numba uses to optimize your Python code, and then when you first run a function decorated with Numba's just-in-time JIT decorator, LLVM generates optimized machine code. This code is then reused in subsequent calls, which is an essential factor to consider in performance benchmarks. What's truly remarkable about Numba is that you can activate these optimizations just by adding a single JIT decorator above your function. This simplicity is amazing because it turns standard Python functions into highly optimized code that can execute at speeds comparable to compiled languages, all without needing to change your code base. This blend of ease and power makes Numba a valuable tool for enhancing Python capabilities in scientific computing. When using Numba to speed up Python, it's important to know what it does best and where it might be not as effective. Numba is great for tasks that involve a lot of numbers, like operations with NumPy arrays, which it can speed up significantly. However, Numba has its limits, especially with more complex Python features. For example, using dictionaries or creating classes and objects common in Python can pose challenges for Numba, as it doesn't fully support these object-oriented programming elements. Numba works best for functions that are used over and over again. For tasks that are run only once or very short scripts, the time it takes to set up Numba might not be worth the speed gain you get in the end. This means you have to think strategically about where to use Numba in your projects. Also, not all Python libraries work smoothly with Numba. Sometimes you might need to find workarounds or stick with slower Python solutions for certain parts of your code. In summary, using Numba effectively requires a thoughtful approach. You need to identify where it can really improve performance and where a different approach might be better. Despite these challenges, Numba is a powerful tool for making Python faster. Now let's see how all our Python coding and Numba speed improvements really work on a computer. We will look into assembly language, which is the basic language that computers understand. This will help us to see clearly how the improvements we talk about make Python faster. Assembly language is very close to the computer's own language, machine code. It shows us exactly how the computer is instructed to perform tasks. To convert high-level languages like Python and C into assembly, we use compilers. CLang is a compiler that processes C and C++ code and uses LLVM as its backend to generate optimized assembly language. Similarly, when we use Numba for Python, LLVM plays a crucial role. We will examine a simple example to better understand this process. By comparing the assembly output for C code using CLang and Python code using Numba, we will see the precise machine instructions involved. This comparison will highlight the efficiency of the code under the optimization provided by the LLVM. In our experiment, we delve into a core operation of computing, summing of two arrays. To the left is the C implementation named mySum, iterating through the array elements to calculate their sum. This code is compiled using CLang with specific optimization flags like O3 and mArchNative to produce highly efficient machine code tailored for the current architecture. On the right, we present the Python counterpart, optimized using Numba's just-in-time compilation with ngDecorator. This setup ensures Python enjoys similar optimization advantages. What's particularly interesting is how we examine the assembly language output for each. For C code, we generate the assembly listing using CLang with the command shown, which outputs the assembly code into .s file. Meanwhile, for the Python code accelerated by Numba, we utilize the inspect ASM method, which is a powerful feature of Numba that reveals the assembly code post-optimization. In this part, we will look closely at the loop within the assembly code. This code is what our high-level Python and C functions turn into when they talk to the computer's CPU. Assembly language is very close to the language that CPU understands, where each instruction does a specific job. This includes doing maths, accessing memory, and managing the order of operations, essential tasks that CPU handles. Here we see instructions like vMoveSD and vAddSD, which move and add data. These are part of single instructions multiple data architecture that helps speed up our calculations by processing multiple data points at once. We manage the loop with cmpq, which compares the values, and GNE, a conditional jump that repeats loop until we have gone through all the data in the array. Both the C code and Python code optimized with Numba end up with similar assembly instructions. This shows how well LLVM can optimize code to make it run faster, no matter the language. By looking at these instructions side by side, we can see how complex tasks from higher level languages are simplified into commands that the CPU can quickly execute, making full use of the vectorization to enhance performance. In conclusion, our detailed look at the assembly code for both C and Python using Numba has shown us some important things. Most importantly, we've seen that Python, when enhanced with Numba, can be as efficient at the machine code level as C. This is immersive because Python is usually more dynamic and runs differently from C. Both C and Python use LLVM, which helps ensure that Python functions are just as fast as C functions. This shows that Numba successfully closes the usual performance gap between compiled languages like C and interpreted languages like Python. Additionally, both the C and Python assembly codes use vectorized instructions, which are advanced optimizations made by LLVM. These optimizations speed up our code by fully using the computer's capabilities. Essentially, Numba lets Python programmers use high-performance computing features without leaving the Python environment. This proves that with the right tools, Python is not just flexible but also incredibly powerful in performance. As we move to practical challenges, let's explore a real problem many of us encounter in fields like high-frequency trading, weather monitoring, and other scientific data analysis. Imagine we have a time series with 10 million data points. While this sounds huge, it actually represents about 9 years of data if we record something once per 30 seconds, on average, starting from early 2015. One key challenge we face in this dataset is its non-uniform timestamp distribution. The intervals between data points vary, which raises a complex question: how do we efficiently determine the maximum value for each point over the next 24 hours? While there are various shortcuts like pandas that offer quick fixes, today we'll focus on more foundational method. This approach gives us full control over our data handling and optimization processes. Let's start by examining a basic, naive solution to this problem, and then discuss how we can optimize it to be more efficient. Starting with a simple approach helps us to set a baseline and understand the demands for our task. Our basic method, maxValues, goes through each timestamp in our dataset, looking for the highest value within the next 24 hours. While easy to understand, this method is not very efficient due to the uneven timings of our data points. In the worst cases, this could make our process much slower, almost quadratic in time. Let's visualize this on the screen. For each data point, we scan forward to check timestamps and find the maximum value within our specified window. This straightforward approach is computationally heavy. In preliminary tests, this method took about 3 hours and 43 minutes to run through entire dataset, a time too long for any situation where quick decisions are necessary. But with just one simple yet impactful change to our basic method, we see a tremendous improvement in performance. By adding the ng decorator from Numba to our inefficient solution, the execution time dramatically drops from 3 hours and 43 minutes to just 235 seconds. This shows the power of Numba's just-in-time compilation, an incredible boost around 57 times faster, all from just one line of code change. Notice how just one line of code with Numba can greatly speed up even a computationally inefficient solution. It requires no extra effort but can significantly enhance performance. However, our quest for even better efficiency doesn't stop here. Let's see how we can further improve our computing methods. Those of you who like to dive deeper might wonder if there is a better way to solve this problem than the quadratic algorithm we've discussed. Indeed there is. We can use some smart strategies from computer science textbooks, but don't worry if you're not familiar with these methods. Just think about their purpose. We will use special tools called maxstack and maxq to quickly manage our time series data. Think of maxstack as the core part of our solution. It's a special kind of stack that always knows the highest value it has encountered. Whenever we add a new element, it checks, is this value highest so far? If it is, the new element becomes the top value. If not, the previous highest element stays on top. When it's time to remove the element, we're not just throwing away data. We're carefully updating our records to keep track of the highest values. This way, maxstack acts like a detailed log, keeping precise track of data and time. Now let's talk about maxq, which cleverly uses two stacks to form a queue. This setup is perfect for continuously checking the highest value over a specific period as we move through our data. Think of maxq as a clever combination of two stacks named S1 and S2 that work together to keep an eye on the highest values over time. When we add new data, it goes onto S1, where we track the highest value looking ahead. When it's time to remove the oldest data, we take it from S2, which gives us the highest value looking back. If S2 runs out of elements, we transfer the elements from S1 to S2 but flipped over, so we always know the maximum. Now let's put our data structures to work. Here's how we use the maxq to derive linear solution to our time series challenge. We iterate over our timestamps, adding values to maxq. As we move forward in time, we continuously calculate the maximum of the values within 24-hour window. When a timestamp falls out of the window, we pop from the queue, which adjusts the maximum accordingly. This approach is powerful. It doesn't matter how irregular the intervals between timestamps are. Our algorithm remains linear in time, making it exceptionally suitable for large datasets where traditional methods fail. With this solution, we've turned our few-hour task into one that completes in 50 seconds. Now we're ready to supercharge this approach with Numba for even greater performance gains. Now we've reached a critical point where we will maximize our solution's performance using Numba. As we refine our Python code with Numba, we need to adjust it a bit. Numba works best with a straightforward procedural style of coding, much like the C programming language. To make the most out of Numba, we will transform our existing class-based setup into a simpler function-based style. This doesn't change the core logic of our solution. Instead, it aligns our code with Numba's way of doing things, which involves just-in-time compilation. By adapting our code to fit this procedural approach, we ensure that we keep the efficiency of our original algorithm while preparing it for Numba's powerful optimization capabilities. As we shift our Max stack from using classes to a more straightforward procedural style, we take advantage of tuple unpacking in Python. This method lets us quickly break down a tuple, simple data structure, into separate variables. This technique helps us keep our code clean and simple while adapting to a procedural format, which is usually more complex. Additionally, it's important to note that Numba works similarly to a layer on top of C, which is a language with strict typing rules. In this environment, each data array must contain only one type of data. We make sure to set up our arrays to meet Numba's requirements, specifying the type of data they hold right from the start. Just like our Max stack, our Max queue also needs to change a bit to work well with Numba. We will transform our dual stack queue into a simpler format that Numba can handle efficiently. Switching our approach to a Numba optimized method was a major step forward in making our calculations faster. We changed our code to a simpler style that Numba prefers, similar to how programming is done in C. This change was crucial because it made our code run much faster, using Numba's just-in-time compilation. What was the outcome? Our time series data, which used to take much longer to process, now takes only 11 seconds. That's more than just 4 times faster than before. This big improvement shows how powerful Numba is. It helps Python perform as fast as more traditional low-level languages. As we conclude our presentation on speeding up Python with Numba, let's review the impressive results we've seen. Starting with a basic solution that took over 3 hours and 43 minutes, we managed to reduce that to just about 4 minutes by simply adding the engine decorator from Numba, a 57x speed improvement. But we didn't stop there. We also refined our approach with a linear algorithm, further optimizing it with Numba to achieve final boost of 1251 times the original speed. This demonstrates the powerful impact of combining efficient algorithm design with advanced computational tools like Numba. This journey illustrates that significant enhancements are possible even with simple intervention like adding Numba to existing codebase. It's a clear example of how, with the right tools, we can achieve remarkable efficiency in Python, encouraging us to think beyond traditional methods and explore the full potential of just-in-time compilation in scientific computing. Thank you for joining me in this exploration. I hope it inspires you to integrate Numba into your projects, pushing the boundaries of what you can achieve with Python. I'm open to any questions you might have, so please feel free to ask.